Recording in progress.
Okay. Lucas, are you around? Lucas?
Yes, I'm here.
Okay, so I'm gonna ask you to chair the 3 talks of this afternoon. Is that okay?
Perfect. Yeah, no problem.
You did a so great job last time that, and we be here in the audience. So let's start the section of this second section of the day, seminar 6 of code items, and I'm passing the position to Lucas Madeira, which is a young, brilliant scientist. Go ahead, Lucas.
Well, it's the first time that I saw that a chair has an introduction, so thank you, Vanderlei. So for this second session today, we have Alexei Akimov. And Alexei, you have 30 minutes. If you want, I can give you a warning 5 minutes before the end of your talk. Is that okay?
Yeah, that would be fine.
Okay, thank you so much.
Thank you, Lucas, and thank you for inviting me on this conference. So, let's see, now my computer doesn't want to cooperate. Okay, so we are working here in Russian Quantum Center trying to build a quantum simulator with ultra-cold thulium atoms, and generic motivation of this work is trying to understand complex materials. So, of course, we're surrounded by many materials that are changing every day, and many of these materials people just have models for, and if they need to change some properties, they change some parameters and get new material. But there are materials which are much harder, and even quantum mechanical computations do not help to understand them and to change their properties even way we want. And some of those are superconductors, for example. High temperature superconductors are out there, and in normal pressure we can see them at around 140 Kelvin. But we don't really know how to get them to room temperature. In fact, we have some at room temperature, but in very high pressures, and there is still open question how to bring those to normal conditions, more or less. And the reason why it's so complicated to calculate is just the complexity of quantum mechanical problem, and it turns out that the equations are on large enough number of particles are very hard for modern computers. And another example is magnetic materials. So for magnetic materials, one of the nice examples of complexity is flustration. So if you have even only 3 particles and you flip one of them, then there is a conflict which one you should flip. So they kind of there will be always one pair which want to be the other way. And that means that you need to, instead of use some simple ground state or excited state, you need to use some superpositions, which exponentially complicate computational problem. And for problems like this, Richard Feynman a while ago said that, like, if you cannot compute a problem, maybe you should not. Maybe you should let quantum mechanics do it and build a toy model of problem you want to solve, in which you can control the parameters, make it evolve on a human scale, not in some picosecond or attosecond scale. And by tuning all the parameters, you hopefully, and letting the system evolve, you hopefully can understand it. And you can use this approach not only for understanding materials, but also for understanding nuclear interactions, for modeling phonons interactions, for understanding turbulence. That's, I think, what our ex-chairman often was doing, or even to understand the early universe. That's also crazy, but seems to be possible. So I really like this work by Markus Reinen, who showed analogy between optical lattice and a crystal field, and said that, look, if we have periodical potential here and there, that means that we can model one system by another, but he went further than that. He also said that, like, as well, we can model magnetic materials by directly observing our atoms, and if our atoms have some magnetic moment or some analog of magnetic moment, then we can, by changing temperature of these atoms, observe, for example, transition from ferromagnetic to antiferromagnetic state, or observe many other different magnetic phases. So that's our instrument. So nice instrument to use is atoms and optical lattice, which hopefully will help us to understand many problems in the material science. Now, which atom to use? So, of course, normal people will use some atoms in the beginning of periodic table, which been already cooled down and well understood. We do not believe ourselves to be normal, so we decided we need to go to some exotic atom, and we picked thulium atom. The reason for that is thulium atom has F electrons, and those are responsible for so-called Feshbach resonances, for some tool we're planning to use to control interaction between our atoms. And also because you have F electrons, you have magnetic moments. So you have atom which has a magnetic dipole moment and has some tunable interactions in which, you know, compared to other atoms in the same row, thulium is rather simple atom, and it has not as complex structure of level transition, and it turns out also for Feshbach resonances it's not as complex structure, so it seems to be more controllable than others. But in order to do something like simulations, we need first to design some initial steps. So if we want to observe evolution of the system, we need to start somewhere, and Bose-Einstein condensate seems to be a very nice point to start, because we can have all the atoms in the same state. So condensate happens when the distance between atoms becomes comparable with the wavelengths. So in this situation, atoms drop in a state which has sufficiently temperature of 0, and all the atoms are described by the same temperature. And that means we not only have the same state for system, but we're also deeply in a quantum mechanical mode, if you want, like all particles are more or less behave like waves, and that's what actually happens in the solid state, so it seems to be a good starting point. Now, the problem with a condensate is that if you just try to cool down things, and normally we have this kind of diagram for metals, so if you're starting from vapor and just reduce the temperature, you should end up with a metal, not with some kind of Bose-Einstein condensate. And this is, of course, because of three-body recombination, so we have collisions between our particles, and if they collide, they like to form molecules and eventually form metals. So that's something which needs to be avoided in our cooling procedure. Then we can reach condensate state and further do some simulations. So level structure for thulium atom looks approximately like this. This is, of course, not all transitions, but only ones we're using. So we're doing primary cooling on this transition, call it 10 nanometers. And then magneto-optical trajectory rate is 530.7 nanometer transition, which is a little bit longer lifetime transition and allows collect many atoms at a relatively low temperature. Now, a nice thing about thulium atoms that it has this doublet structure, so hyperfine interaction is nearly the same in ground and excited state, and it only only have these doublets, and it kind of simplifies work with it, and also like it's not that many levels, even though there is still quite some. So primary cooling steps are standard. So we're doing Zeeman slowings, and we're doing magneto-optical traps, and we follow an idea suggested by Francesca Pelaina. We detune our magneto-optical trap to large detuning, and then because detuning is now too big, atoms only are cooled near the surface of the sphere, which is a point in which detuning compensated by magnetic field in a magneto-optical trap. So it's supposed to be like shallow trap now, shallow sphere, hollow sphere, but because of the gravity, all atoms are kind of dropped to the bottom of the sphere. So instead of being a hollow sphere, we have just this smiling face. And what it helps to only make all atoms interact with one beam, which is supporting this trap, and in fact optically polarize them. This way we removing all necessary internal degrees of freedom and concentrate atoms in MF equal to -4 state. So we're getting up to the 10 to the 8 atoms in this trap with the temperatures around 10 to 20 microkelvins. It slightly depends on the parameters. But then, of course, we need to cool them further, and active cooling is not very efficient. So we are using evaporative cooling where we basically wait. So we're basically waiting while atoms collide, and from time to time, some atoms should have high enough energy to leave the trap, and then the rest will thermalize and have lower temperature. So in this sense, we actually, for this cooling mechanism, we do need collisions, but we want two-body collisions, not three-body collisions. So now question is, how long should we wait? And of course, the best is to wait forever and get just one atom to like carry away all the energy of the trap. But that's impractical because, first of all, there are losses of the trap, so trap doesn't really live longer than some seconds. And also some students somehow want to get some PhDs out, so you need to expedite this process, evaporate them faster. So we need to reduce depth of the trap to make evaporation faster. And then there's a very large number of questions. So one is how fast we need to change this depth of the trap. There are other technical questions like magneto-optical trap. The way we're doing it, it's few millimeters, and optical dipole trap, which you use to cool down atoms in an evaporative way, is just some tens of microns. So there's really bad overlap between two geometrically. So in order to solve it, we're starting to scan our trap through the magneto-optical trap, but then how much you scan, where you should stop, when you should start to do your change your intensity. That's all questions of optimization. And also, because we want the distance between atoms to be small, we need to add another beam, vertical beam, because in a single dipole trap, atoms are not really localized that much along the beam. To compress them, we add in second beam, but again, the question when exactly we add this beam, how we change intensity. And those are all very interesting questions, and people have some idea how to solve them, but it turns out to be not very easy when you have that many of them. And what we found to be useful, and it's actually was idea which I borrowed on one of the LPHYS conferences. I think it was in Nuremberg. Maybe it was in England. Doesn't matter. So idea is to use machine learning to optimize procedure for cooling. So instead of trying to ourselves find all these optimal trajectories, how and when to turn on things and to reduce the intensity, we decided to feed it to the computer. And the parameter we were optimizing in our first experiment was this gamma parameter, which is logarithm of how much of phase density you want compared to what you had initially, divided by logarithm of ratio of atoms, basically like what price you paid to get this increase in phase density. And it's this minus sign to make it positive. So what we have done, we asked the computer to generate sequences for all our laser beams and all our like switching procedure and everything, feed it to the setup, and then got a picture of the cloud at the end of all the sequences, feed it back to the computer, and ask computer to optimize the sequence. So before doing that, of course, we tried by hand, and it didn't quite work. We didn't got the condensate, but we did got some cooling, and gamma optimized by hand was around 0.8 over all cooling steps. And then these sequences was fed to computer as the best we know, and it started to change randomly sequences around this point, and immediately, like from this random search, it found that you can do actually better. That human being are stupid enough to not find it. And then after making some number of random steps, about 40 in this case, it started to use accumulated knowledge of these trials to predict where sequence should go, and started to gradually improve. Of course, not every step is improving. Sometimes it's doing false runs, but it's all added to statistics. and eventually this gamma factor improves. And what we found that with a computer, we can, instead of 0.8, get 1.6, which is double of what we had by hand. And that's the difference between having condensate and not having condensate. So it's interesting that part of the problem is in a way how we measure things, because when we measure phase density in the cloud on different steps, we have different size of the clouds and we have different techniques. And sometimes we have some crazy things like this, just switching from one technique to another. We don't have continuous graph. And this is just problem of how we do an experiment. But in reality, computer only looks in the beginning and the end. It doesn't really try to, measure all these steps in between. And that's one of the things why it's optimizing much better than a human being. It doesn't have all these experimental difficulties. It always has two fixed points, endpoints in beginning and optimizing through them. But of course, there are things which human being would not do. For example, in the beginning, there is a heating, which normally we, of course, will try to avoid, but computers say it's actually better. There are also some kinks somewhere which are not due to experimental measurement things, but like just happen to be optimal. So we, the way we know we got was Einstein condensate, and the way computer was deciding that it has condensate is by showing, seeing this distribution with a thermal cloud and parabolic shape in the middle. So once we have this parabolic shape, kind of know that we have condensate. But of course, even though computer was making decision based on these pictures, we need to prove that it's actually condensate. And one of the properties of the condensate is its coherent state. So it should evolve similar way to way laser beam evolves. So if we have a shrink this condensate in one direction, it should expand faster in this direction. And that indeed what it does, if we release a cloud, it expands faster in the direction in which it was compressed the most. While thermal cloud doesn't do that, thermal cloud always expands with the average velocity. So eventually, even if there was some shape originally, it will go to the sphere and expand to the sphere, expanding with the same velocity. And that's quite a huge difference, which are easily observed. So we know we have something coherent. Of course, there are other things to check. So we, for example, can check how number of atoms depends on the temperature versus critical temperature. And you see that's really nicely follows the theory. In that experiment, error bars were rather big, so we couldn't distinguish theory with and without dipole interaction, but we at least show that we do have condensate. Now, once we got a condensate, we started to think what actually we go into model, and we talked with our theoretician, George Shlyapnikov, who said that what he is interested in right now is a Hubbard model with disorders. So we need to build a periodical system in which we have interaction on site, which we can control and open from one side to another, and then add some disorder to the system. And that kind of implies that we better have single site resolution, so we better be able to observe each single atom in the system. And we figured that even though originally we started our experiments in a 532 nanometers dipole trap, half-wavefront of that is 250 nanometers, it will be really hard to see each side, and especially to create disorder potential on each side with a single site resolution. So we need to somehow enlarge the system. So we started to think about how we can switch to maybe longer wavelengths. And we decided that we, instead of doing it in 532, we will switch to 1064, which is actually more common in the community. But in terms of building this quantum dot microscope, it seems to be advantageous. And it's different in many sense, because at these wavelengths we have Fuzz-Font transitions. So we have only scalar polarizability, which we measured, and don't have much of a tensor and vector while when we're working at 532, we have a lot of tensor and vector one, which has some advantages. We can do site-dependent lattices this way. Here, we don't really have that handle, but we have better optical resolution. What we met at that point is that we switched, from 532 nanometers to 1064. It's factor of 2 change in wavelengths. Of course, our windows were anti-reflection coated, but they were anti-reflection coated for 532. That's by definition is mirror for 1036. It's not that bad because there is dispersion in the materials. So in reality, our mirrors were only like 20% mirrors, not 100% mirrors, how one could expect. But still, we had unwanted reflection in our lattice, which we had to live with for some time. And we wanted to understand if we, for example, built a lattice by crossing two beams of 1064 nanometers, do we actually have any contribution of this reflection or not? How to measure it? We need some sensor inside the vacuum volume. And we figured we have Bose-Einstein condensate there, so what could be the better sensor? So if we let Bose-Einstein condensate to see our lattice for some time, then it is predicted that we should see diffraction pictures like this or that. Those depend on many parameters, like how long you expose and what is the depth of your lattice and stuff like that. But anyway, the period between these spots should be always momentum of the lattice. And then there is some evolution which is more or less described in the series. Now, picture on the right is actually lattice we wanted. We were able to measure indeed the period of lattice watching our expectation, and all these spots in the diffraction picture nicely match to what we would expect. But picture on the right is actually picture with one beam blocked. So we blocked one beam, and we still see some diffraction pattern. It's in a different direction. Here it's vertical, here it's horizontal, more or less, but there is still diffraction, which means we do indeed have reflection. And we did it for both beam, and only one of them had it, and another one didn't. But that's not the lattice we want. That's lattice we wanted to remove. We didn't really want it in our experiment. So we started to analyze like how much we need to change angle of our beam. And in our experiment, we kind of plane everywhere around 16 degrees. All these beams are crossing, have angle of 16 degrees with horizontal. So 16 degrees is kind of our zero level. And what is the conditions that we have a lattice? Like why Bose-Einstein condensate, when Bose-Einstein condensate will see lattice? It turns out it's very simple. So you need to have at least one recoil. So if you have one recoil, then you see a lattice. If you have potential which is smaller than one recoil, then Bose-Einstein condensate to ignore your lattice. And we can from that calculate what order of this diffraction gradient we will have. And it turns out to be this formula, which was not derived by us. We actually took it from literature. And setting this number to 1, saying like, look, we got to have at least one recoil to see the picture. We can say at which angles, by just calculating geometry and calculating optical depths, are our beams. It turns out that we should be only 0.2 degrees off from normal incidence to completely avoid our unwanted lattice. In fact, after doing this work, we understood that we can actually, using these equations, measure exactly what angle was. We have not done it at that time, but actually a condensate diffraction image has enough information, if you especially change factors like exposure and stuff, to understand exactly what you do. Now, there are other interesting differences. So, for example, in 532 nanometer strap, it's actually close to one of the cooling tradition we use. So we were like always worried there is some heat in there. And we measured lifetime of the trap, and we see it lives for about 5 seconds. We measured heating rate, and it's kind of like almost explains this lifetime. So it's kind of close. So we can make a conclusion that, yeah, probably, there is some heating. But once we do the same experiment for 1064 nanometer strap, we see that actual lifetime is the same. We don't really gain anything. It's slightly longer, but not much. And there is still some heating rate, but it cannot be explained by photon absorption at all. So theory doesn't just make any sense. So it looks like that in reality, limiting factor is something else. It's maybe stability of our acoustic optic modulators or something else. So we do heat our system somehow, but it's definitely not the photons which are doing that. It's some probably mechanical instability of the atom. Now I have only a few minutes left, but we also tried to use Feshbach resonances to control interaction between our atoms. So idea is very simple. If two atoms are approaching each other, then there is an orbital moment between them. And if we're cold enough, barrier which exists due to this orbital moment, basically due to the fact that two particles can pass each other without actually colliding, becoming large at lower temperature, and we expect only have S collision, not really collisions with a high angular moment. And for these S collisions, nevertheless, because we have internal degrees of freedom, we have different MF levels, we can expect that even if we are colliding here in open channel, there's obviously no levels here, different closed channel in which we don't have atoms, but it might have bound state with different MF, which is related or equal in energy to energy of incoming atom. And of course, then we can tunnel for some time to the state, then decay back, and that will cause a resonance, which is called Feshbach resonance. And those can be used to tune scattering lengths of atom in a very wide range. And it may become so high that we will start to again see three-body recombination, which we were trying originally to avoid, and we will see losses of number of atoms. And those could be seen nicely. We see also that they depend on the temperature. And first we were thinking that it's just, nice theoretical fact that in these lanthanoids at a large enough temperature, you can see larger orbital momentums because there are these F electrons, and they allow appearance of these large orbital momentums at a rather low temperatures, and you can see collisions, not S collisions, but rather like D or H collisions entering into the system and analyze the statistics and such. Later we understood that those are actually very important because they not only appear at higher temperature, but also in a higher density. And information we got here at high temperatures is actually now very useful for us trying to understand which point, first of all, to avoid when we're cooling, when we're manipulating our condensate. Condensate has high density, and those things appear in the condensate, and also how to tune our resonances. So our plans is to now, with all this done, to load our optical trap with some 1,000 atoms and try to do this Bose-Hubbard model with a disorder. There are still few pieces missing, but we are very close to start actual simulation. This is team which is working on this project. And with this, I thank you for your attention.
Thank you, Alexei. I didn't interrupt you because when I was going to give you the 5 minutes warning, you were kind of concluding. Do we have any questions? Well, maybe I can start.
I have a question.
Okay.
Yeah, when you use the machine learning to optimize the conditions, once the computer found the best route to get the condensate and the optimized condensate, do you still keep using the machine, or you made a kind of a map and you make sure the system goes to the route that was optimized? So
yeah, that's an excellent question. So we use optimizer to find a route, and then we just use the route. So we don't use it every day, right? Now,
do you think that the computer will find a new route every day?
That's what we're doing right now. We first, find the route, then we changed wavelengths of a dipolarizer, and the route still worked, very robust. So same route for different wavelengths of dipole trap still works. Nice. But now we decided we want more atoms in the condensate. And we started to run optimizer again, and it's work in progress. But it turns out we can do even better. But there were some parameters we were not touching, and now we're starting to touch them. and we're actually improving. So root stays very nicely for a very long time. But finding a global optimum is a very tricky thing, it turns out, in the system. Even with optimizer, if you didn't let it enough freedom, finding just some local minimum. And this number of parameters is larger than you think, always, you know.
Yeah, no, I thought. Thank you very much.
Are the flashback resonances for Thulian well known? Are you mapping this right now? What's the status?
We just map them, so they're not known. You cannot predict their position. You can predict their statistics, but you cannot really calculate where they will be because of the complexity of the system. So we measured them at different temperatures, and it appears to be very useful for us right now. So it's a very important piece of information which allows us to change the scattering length of those, and also to know where you should not go, which magnetic fields have a lot of losses and stuff like that. We did analyze their statistics, and we figured that they have random statistics almost at low temperatures, but they becoming more chaotic, like it happens in dysprosium and erbium at higher temperatures, and unfortunately in higher densities too. But nevertheless, the fact that we have this random statistics tell us that they're, at least at low densities, low temperature limits, they do not really interact with each other, and we have relatively high degree of control of scattering lengths.
And do you have plans to study FMOS physics in the system?
In principle, yes. In principle, yes. But like our first target right now is to complete this Hubbard model experiment, and that's already given us a lot of headache. So probably in a few years.
Right. Thank you. Do we have any more questions for Alexei? No, if not, let's thank him again. And our next speaker is Matteo Caldara.
Yes, here I am. Can you hear me?
Yes, we can hear you. We can see your screen.
Nice. And let me set the pointer.
Perfect.
Okay.
So if you like, I can give you a 5 minutes warning before your talk, your time's up.
Yes,
I'll
please.
try not to interrupt if you're saying or concluding, okay?
Okay, thank you.
Thank you, Matteo.
So, thank you, Lucas, and thanks to the organizer for giving me this opportunity to present some of the main results that I've collected in a recent work that I've realized in collaboration with André Richaud and Pietro Massignan from UPC in Barcelona, and together with Massimo Capone from SISSA in Trieste. So, the main actors of this talk are quantum vortices, that are topological excitations around which a quantum fluid exhibits a swirling flow. And they are characterized by two main properties that are the density depletion at the vortex core and the quantized circulation of the superfluid velocity going around the vortex core. There were plenty of experimental detections of these topological objects, starting from a superfluid liquid helium-4, then passing through type 2 superconductors, and also finally to atomic Bose-Einstein condensates in the early 2000s. So in a uniform system, a large number of vortices are arranged into a very ordered configurations that are the ones of the two-dimensional vortex lattices. Then restricting to 2 dimensions is of particular interest because in these configurations, we can get rid of the extra degrees of freedom associated to the vortex line bending, and basically everything boils down to the study of the dynamics of point-like vortices. So this field of research has gathered a lot of attention since the beginning of the last century with the study of classical incompressible non-viscous fluids. After that, it found a lot of applications in purely superfluid systems, such as helium-4 first, and after that also in dilute atomic Bose-Einstein condensates. So, as you can read in a very nice recent review by Andrea Tononi and Luca Salasnic, the study of vortices in various curved geometries turns out to be a promising research area. In particular, let me stress the attention on here on ellipsoids and spheres, because they are strictly related to the experimental possibility of achieving bubble-trapped Bose-Einstein condensates, for instance, in the NASA Collatom Lab on the International Space Station. Among these curved geometries, there is, for instance, the surface of a cylinder of finite height. And I remind you that such a surface is topologically equivalent to a planar annulus geometry. In fact, these two surfaces are connected one to the other by means of a conformal transformation. Another very interesting and recent area of research, as already outlined by Andrea in yesterday's very nice talk, is to try and discover the role that is played by finite core mass in the dynamics of these vortices in two-dimensional configurations. So, given these three elements, if we put them together, what I can say is that the study of the dynamics of massive vortices inside the superfluid annulus turns out to be an interesting starting point in order to proceed towards a better grasp of the interplay between the mass, topology, and geometry on a generic curved surface. So after this motivation, let's say, of our work, let me give a very brief introduction about the superfluid vortex dynamics in order to set a common notation that I will stick with throughout the whole talk. In particular, we all know that a superfluid can be described in terms of a macroscopic condensate wave function, in terms of a density field and a phase field. The velocity of a two-dimensional superfluid can be equivalently written in terms of the gradient of the phase field, or after introducing a scalar stream function that is particularly interesting because the velocity lines of the superfluid corresponds basically to the streamlines that are the lines of constant stream function. We know that the superfluid satisfies the irrotational condition, but then if we also assume the superfluid to be incompressible, and notice that is a quite fair assumption that is indeed satisfied in helium-4 and also in Bose-Einstein condensates within in the Thomas Fermi regime, then we also have that the velocity of the superfluid is divergenceless. By putting together these two properties, it turns out that these two scalar functions, that are the stream function and the phase field, have to satisfy the Laplace equation everywhere apart from the points where we have the phase singularities represented by the vortices. This Laplace equation then has to be implemented by the correct boundary conditions for the superfluid velocity at the borders of our system. So, the take-home message is that the study of the massless vortex dynamics in two dimensions, since it is equivalent to solve the Laplace equation, displays a very strong analogy with simple electrostatic problems of point charges moving on a plane. Given that, we can make use of the complex potential formalism. So if we consider a bunch of vortices on a two-dimensional plane, then we can label each of them with a sort of complex position that is given here, and then introduce a complex potential that is a meromorphic function whose real part is the stream function, while the imaginary part is the phase field. With two ingredients, the velocity of each vortex is given by this very simple formula, where we can see that the derivative of the complex potential is nothing but the superfluid velocity, and we have to subtract from it the divergent contribution coming from the vortex itself. This formulation is completely equivalent to a more standard and common tool that is the one that is usually used to describe vortices in two dimensions, and that consists in using a point-like Hamiltonian, where the only relevant quantity that we need to know is the total energy that is given by the interactions between each vortex and the boundaries. Notice that such an interaction can be recast in terms of image vortices, exactly as in electrostatic problems, and also taking into account the interaction with the other possible physical vortices that may be present in our system. So once the total energy is known, then it turns out that the dynamics of these vortices in two dimensions is described by first-order equations of motions. And in particular, this formulation at the bottom of the transparency is nothing but the vectorial representation of this expression given in terms of the complex potential formalism. Let me stress among all the properties the very important fact that within this framework, the x and y coordinates of each vortex play the role of canonically conjugate variables. It will be very useful in the following. In particular, if we consider the specific case of a single massless vortex that is located within a planar annulus, then in order to implement the correct boundary conditions, meaning that the velocity of the superfluid has to be tangent at both the outer and inner border of the annulus, we need an infinite set of image vortices that are represented here with the blue and red dots. In particular, these images arrange themselves with alternating charges, both in the outer part of the annulus and also in the inner part. As a result, we can see here in this contour plot, the phase field that correctly changes by 2 pi as we go around the vortex core that is represented by the red dot here. The white lines then represent the streamlines that are the velocity lines of the superfluid. And we see that they correctly whirls around the vortex core and that they are tangent at the borders of the annulus as required. If we apply then the simple recipe that I showed to you in the previous slide, we obtain that such a vortex undergoes a very trivial dynamics. That is a uniform circular motion with an angular velocity that depends on the radius of the circular orbit here. The functional dependence of such a velocity on the radius of the circular orbit is shown here. And as you can see, due to the fact that we have two boundaries, then first of all, the velocity diverges at the boundaries, because in this situation, the vortex would annihilate with the closest image. But then there is also the possibility for this velocity to change sign. In particular, if you place your vortex exactly at the geometric mean between the inner and outer radius, your vortex will stand still. So up to now, I presented to you nothing new, and I talked about what they are usually called as massless vortices. But now let us shift the gears and consider the fact that, actually the vortex cores may be filled. In particular, this is the case of whenever we have impurities, and for instance, this is what happens when ions and solid hydrogen are used as tracer particles that play the role of Bragg scattering sources in order to allow the vortices in superfluid helium-4 to be experimentally detected. Another important example, in my opinion, is the fact that these massive vortices actually were present already in the first experimental detection of vortices in a Bose-Einstein condensate that took place 23 years ago in Cornell's group. In particular, they dealt with two hyperfine species of bosonic rubidium-87, and they observed that the second minority component went and filled the vortex cores of the first majority one. So, given that, the basic question that I would like to address now is, how does an effective mass affect the vortex dynamics? In order to answer, let me sketch to you the physical system we are considering, that is a planar annulus with inner radius R1, outer radius R2, and that is completely filled by a first species that we label as species A, that is a superfluid hosting a point vortex at position R0 inside the annulus. We allow then for the presence of a second species, species B, that is actually trapped inside the vortex core. So this is a very important assumption, that is the fact that the species B is localized within the vortex cores. It turns out that the only relevant parameter to describe the dynamics of these massive vortices is the ratio between the total mass of the species B over the total mass of the species A. So far, we did not introduce any restriction on the species B that may or may not be superfluid. However, if we consider the case of a two-component dilute Bose-Einstein condensate with contact-repulsive interaction, that we need to require this mixture to be in the immiscible regime in order for the condition of localized species B atoms to be satisfied. So we studied the dynamics of these massive vortices relying on a very powerful mathematical tool that is the time-dependent variational Lagrangian method. Let me now sketch the main ingredients of this recipe. The starting point consists in writing down the two-component variational Lagrangian that is a functional of the wave functions of both the species. As you may notice here, we do not have any mixed term as a consequence of the fact that we are neglecting any relative motion between the mass and the vortex cores, since we are considering the mass to be localized within them, meaning that we can use the same set of coordinates to describe the mass and the vortex cores. This is particularly explicit when we go to the second step, That is when we write down the explicit expression from the time-dependent variational Lanzese of the two wave functions. In particular, for the species A, we use a standard hydrodynamic form, where the density field is given within the Thomas Fermi approximation, while the phase field accounts for both the physical and image vortices. The wave function for the species B is a superposition of Gaussian orbitals that are pinned exactly at the position of the vortex cores in the species A. When we put these two ansatze inside the Lagrangian functional and we perform the integration over the field variables, we end up with a Lagrangian that is a function only of the coordinates and velocities of the physical vortices that live within our annulus. In particular, such a Lagrangian is made by a first contribution that explicitly depends on the mass and comes out from the species B, and a second contribution that comes out from superfluid species A that contains a one-body term representing the self-energy due to the interaction with the image vortices, and a two-body term that accounts for the vortex-vortex interaction. As a final step, we take the Euler-Lagrange equations from this Lagrangian, and we end up with the so-called massive point-vortex model, telling us that the dynamics of these massive vortices, due to the presence of this completely new, this brand new term here, are described now by second-order equations of motion. So let me be more specific and consider the simple example of a single massive vortex inside the planar annulus. The Lagrangian looks like this, and we immediately recognize a very strong analogy with the Lagrangian of a massive particle moving inside a static electromagnetic field. In particular, the one-body term plays the role of an effective scalar potential, giving rise to an effective non-uniform electric field points along the radial direction. Then we can also single out an effective vector potential from which we obtain a uniform effective magnetic field that pierces through the plane where the annulus and the vortices live, and that is proportional to the superfluid density of the first component. When we take the other Lagrange equations, we end up with the following Lorentz-like equations of motions, and it is now clear that the finite massive core plays the role of an extra inertial term that gives rise to second-order equations of motions. Now, the core velocity is not uniquely determined by its position, and differently from what I told you before, now the x and y components of each vortex are no more canonically conjugate variables. This is very, very important because now we are dealing with a very richer dynamics, and it allows also to perform a decomposition of the overall motion of the vortex into the sum of two circular motions, following a very common approach, a very common tool that is used in plasma physics. In particular, the first contribution comes from the motion of a guiding center, whose velocity is given by the so-called E cross B drift. For our configurations of effective electric and magnetic field, such a drift points along the tangential direction, meaning that the guiding center describes a uniform circular motion that now, due to the fact that we're dealing with second-order equations of motion, can take place at two distinct frequencies. Please notice the fact that the plus-minus here do not refer to the overall sign of the angular velocity, but only to the fact that we have two distinct solutions. And then in particular, the omega minus solution turns out to be the most energetically favored. Such a solution actually, so the uniform precession, becomes unstable whenever the mass ratio overcomes a certain critical value that I label as mu c1, and whose dependence on the radius of the circular orbit is represented in this plot on the right. In particular, this blue region represents the region of instability for such a uniform precession solution. The second contribution to the overall motion is a cyclotron motion taking place with a cyclotron frequency that is proportional to the strength of the effective magnetic field. A particular situation takes place when the Larmor radius is much smaller than the radius of the uniform circular orbit, and in this configuration, the cyclotron frequency reduces to the characteristic frequency of small radial oscillations that can be obtained by performing a linear analysis on top of the uniform precession solution. Even this solution turns out to be unstable when the mass ratio overcomes a second critical value of the mass ratio that is actually a more restringent condition, as we can observe here within this orange shaded area in the plot on the right. So now, in order to gain a better physical insight on the trajectories of this vortex, it is convenient to exploit the symmetry of the annulus, the symmetry of the annulus that consists in a conservation of the total angular momentum, and introduce an effective potential that depends only on the radial coordinate. In particular, if we fix the total angular momentum, we see that the shape of this effective potential depends on the particular value of the mass ratio that we are considering. So when the mass ratio is within the safe region for the uniform precession solution, we see that the shape of the effective potential is such that it has a local minimum, and here we are performing a standard analysis like the one in the usual Kepler's problem. When the dynamics takes place at the local minimum of the effective potential, the corresponding trajectory is a simple uniform precession. But then, as soon as, by keeping fixed the angular momentum, we change the initial conditions, so both the initial position and the initial velocity, we can get through some more interesting trajectories. In particular, if the initial radial displacement is small compared to the radius of the circular orbit, we end up with these small radial oscillations on top of the uniform circular solution. Then, for any generic initial radial displacement, the situation is fancier, and the corresponding trajectory are these spiral-like trajectories whose mathematical definition that are mathematically defined as epitrochoids, but that from now on I will refer to as curly-like or spiral-like trajectories for the sake of simplicity. Then, when we increase the mass ratio, what happens is that the minimum of the effective potential progressively disappears. And in particular, when we overcome the critical mass ratio for the onset of the instability of the uniform precession, what we see is that wherever the dynamics of the vortex is initiated, then the vortex is driven towards the outer edge of the annulus, where it is eventually expelled. So far I presented the analytical results that were obtained within the massive point vortex model, but we were able to benchmark their robustness against the numerical simulation of Gross-Vitaevsky equations. In particular, we considered as a physical system a binary Bose-Bose mixture where the first component is sodium-23, and this is the component that hosts a single vortex. This is a standard massless vortex, let's say. Then the second component, that is potassium-41, as you can see here in the density plot here, is localized within the vortex core of the first component. We then chose the microscopic parameters of this mixture in order to safely be within the immiscible regime condition. Then, this mixture is described by these two coupled Gross-Vitaevsky equations, where there is a density-density interaction, as you can see here with these mixed terms. And what we did was to solve numerically these two coupled Gross-Vitaevsky equations. The numerical results gave us a very interesting, so the numerical results were very interesting because they allowed us to benchmark the validity of the analytical prediction. Here, for the uniform precession, in fact, the points that are the numerical results nicely follow the curves that are the analytical predictions, and also for the more generic curly trajectories. In particular, let me spend a comment about this plot on the right, where you can see the time evolution of the radial coordinate. As you can see here, there is a frequency mismatch between the analytical prediction, the orange analytical prediction coming from the point vortex model, and the blue numerical results. This is basically due to the fact that the numerical results in some way know that we are dealing with many-body Bose-Einstein condensates with some rather complicated internal modes. These internal modes actually are totally missed by the analytical point vortex model, whose only degrees of freedom are the coordinates of the vortices. And the point vortex model basically gets rid of any information about the system where these vortices are embedded into. In the very last part of my talk, I would like to generalize our result to the case of a vortex necklace, that is a particular symmetric configuration of vortices within our planar annulus. Let me mention that the vortex necklace is formed at the interface of two initially separated superfluids that flow with equal but opposite circulation. In the plot here on the left, you can observe the experimental protocol that was used in Florence in the group of Giacomo Ratti and Francesco Scazza to create a vortex necklace using a superfluid fermionic lithium-6 across the BCS to BEC crossover. So we basically applied the massive point vortex model to the case of a necklace. And here you can observe the results for the particular configuration of a necklace made of 4 vortices. As already found for the case of one single vortex, we can have the uniform precession solution and also these more generic curly trajectories on top of the uniform precession. Let me spend in this very last part a few words about the uniform precession. In particular, we found that if you consider a massless necklace, then you can use, for instance, the complex potential formalism. The uniform precession takes place at a single value of the angular velocity, and the functional dependence on the radius of the circular orbit is depicted in the plot here below for different numbers of vortices that make up the necklace, essentially. Here we go from 1 up to 6. These curves are continuous, and this means that such a solution is allowed within the whole annular region. However, when we go and consider a massive necklace, so for instance, here we fix a constant mass for each of the vortices that are present inside the necklace. So first of all, this uniform precession now allows 2 distinct frequencies. But then what we observe is that the curves for this frequency as a function of the radius of the circular orbit are not always continuous. In particular, there is the appearance of a critical number of vortices above which, in this case, this critical number is NB equals 7. These curves split into 2 distinct branches. And this signals the appearance of a region inside the annulus where the uniform precession is not allowed anymore.
Matteo, 5 minutes.
Thank you very much. It's now time to conclude. So within this talk, I presented to you what are new features that are introduced by a finite massive core. In particular, such a finite massive core gives rise to extra inertial term, and that is responsible for equations of motions that now become second order. As a consequence, vortices do not trivially move following the superfluid velocity flow, but they are characterized by a richer dynamics compared to their massless counterpart. Then I presented also a clear electromagnetic analogy that shed light on the fact that during their motion, these massive vortices feel the effect of an effective density-dependent magnetic field that is provided by the surrounding superfluid component. Then let me also mention the fact that the system that we studied is within easy experimental reach by several groups, like the ones in Paris, Hamburg, Heidelberg, or in Florence. Finally, such a work paves the way to address some very interesting open questions about the role of the massive core. For instance, we would like to extend this analysis to study the dynamics of massive vortices on the surface of a finite cylinder. Then we would also like to see whether the mass, a finite mass, would be able to stabilize the vortex chains on a ring that were shown to undergo a Kelvin-Helmholtz instability. And finally, due to the fact that we're dealing with a 2-dimensional geometry, we would like to better investigate the role of the mass in the Berezinski-Kosterlitz-Taulitz physics. With this, I conclude here my presentation. I would like to thank you for the attention, and I'm available for any question. Thank you very much.
Thank you, Matteo, for the very interesting presentation. Do we have any questions? So I can start with one.
Sure.
The difference between your analytical results and the GPE simulations, you attributed that to more complicated phenomena when you're dealing with these condensates. Maybe it could be just the effect of having a finite sized core. I don't know how you could take that into account, but what I'm thinking is you have a vortex of species, the majority species. If you put something inside of it that's repulsive, it's going to get larger. So maybe the cutoff that you had before, you have to increase it. You don't let vortices get so close because it got larger. And you mentioned Giacomo Roati's experiment, which is with fermions. But when you go to the BCS side, I believe these vortices will be much bigger. When you go to the BEC side, they can get filled. So I don't know. Is there some way of taking into account the size of the vortex in your calculations?
So first of all, you are completely right in the sense that the finite size effect is a very important thing, and it is one of the reasons why there is this frequency mismatch between the numerical and analytic results. I didn't mention it, but in the paper we mentioned this fact. So thanks for having clarified this. And actually, there was one of the first papers by Andrea about these massive vortices actually took into account this fact, and they were able to somehow estimate what is the effect of the finite mass into the healing length of into the modification of the healing length of the vortex. In particular, there is a nice interplay between the healing length of the bare vortex, the massless vortex, and the sigma, so the variance of the Gaussian wave function associated to the massive core. So if you're interested, that is I think so far the best and most complete reference where one can have an idea of how the vortex and then also the cutoff that you were mentioning has to be modified to account for a finite mass.
Thank you.
You're welcome.
Do we have more questions? I don't see any hands raised. So let's thank Matteo again for this wonderful presentation.
Thank you.
And now our next speaker is Denis Krizenko. Are you there, Denis?
Yes, I'm here.
Okay. Yeah, now we can see you.
Can you see my presentation?
Yes.
Okay.
If you could put it full screen.
Hello, everybody. The topic of my work is laser cooling of ytterbium ion by polychromatic field without the use of magnetic field. At present time, cold ions are used in optical clocks, which have many fundamental applications. The achieved level of accuracy in optical frequency standards opens up new possibilities for testing of for the development of fundamental researches, such as verification of Einstein's general theory of relativity, definition on physical constants, test of Lorentz invariance of space, and different physical laws, and also search for dark matter. One of the bright example of recent research is the test of principle of local Lorentz invariance, which was done by PTB group. The principle of local Lorentz invariance consists in the invariance of physical laws by rotations and displacements of laboratory reference frame. The post-precision measurement demonstrating local invariance for light propagation was performed by Marcusson and Morley. And the use of optical clocks on cold ytterbium ions allows testing this principle at a higher accuracy level. In the experiment, PTB group has used two optical clocks operating at electrical dipole transitions for testing this principle. Lagrangian of this system was determined by tensor of electromagnetic field, and violation of invariance was determined by dimensionless tensor KF. In the experiment of PTB group, energy shift delta H was measured by comparing frequencies of first and second clocks. The enlarged area at this picture shows a frequency difference of 2 millihertz obtained over 6 months of measurements. It is quite impressive measurement accuracy. And for achieving this measurement accuracy, it is necessary to take into account shifts of atomic levels of different nature. So works aimed to suppression of these shifts are highly relevant. As you can see from the first table, schematic frequency shifts for first and second clocks in different in units of transition frequency are shown in this table. As you can see, second-order Doppler effect, blackbody radiation, and second-order Zeeman effect has a significant influence of uncertainties of these clocks. And in the context of frequency standards based on cold ytterbium ions, the future progress can be related with suppression of shifts related to second-order Doppler effect, second-order Zeeman effect, and as I said before, blackbody radiation shifts. The difference of frequency of 1 millihertz corresponds to the uncertainty of clocks 10 to the minus 18th degree. The feature of laser cooling of ytterbium ions in the trap consists in the fact that optical transition to S1/2 to P1/2 has two energy levels at the ground state and excited state with full angular moments F equals 1 and F equals 0. The main challenge here is that this optical transition is not closed. It requires at least a laser field of two frequency components and magnetic field to for laser cooling. The use of a relatively large magnetic field of 1 to 10 Gauss is necessary to eliminate a coherent population trapping effect at the level 2s1/2 with F equals 1. However, hysteresis effects during shifting of magnetic field create certain difficulties in minimizing of residual magnetic field and keep it in constant in the cycles of cooling and clock operation. The goal of the work is to study alternative methods of laser cooling of ytterbium ions without the use of magnetic field. The main tasks of the work are search for optimal light field configuration and search for optimal field parameters corresponding to the minimum temperature of laser cooling. We consider a polychromatic field which consists of three frequency components. The first field is resonant to optical transition to S1/2 with F equals 1 and to P1/2 with F equals 1. The second field is resonant to optical transition with F equals 0 and with F equals 1. And the third field excites optical transitions between levels to S1/2 with F equals 1 and to P1/2 with F equals 0. The polarizations of fields and orientation of polarization vectors can be arbitrary. In general case, all waves have elliptical polarizations. Hamiltonian of ion in polychromatic field doesn't include interaction with external magnetic field, and interaction with laser field is considered in dipole approximation. One of the main mechanism of laser cooling is a Doppler cooling mechanism. Its idea is a velocity selective interaction of atom with the light. Atom moving in a field of running wave experiences light pressure. If the frequency of laser radiation is less than optical transition frequency, then atom is closer to the resonance with the running wave. Appearing light pressure force in this case is proportional to pulse of the photon of the field and the rate of spontaneous emission. A considered task is more complex than task of laser cooling of two-level atom. The density matrix in this case is a block matrix 4x4. For terbium ions, we have 4 sublevels at the ground and 4 sublevels at the excited state. We can reduce this equation for density matrix in a quasi-classical approximation to a Fokker-Planck equation for a functional distribution with some coefficients. Coefficients of these equations are light pressure force and diffusion. Analytical expressions for these coefficients allow us to get temperature of Doppler cooling and to solve Fokker-Planck equation for a function of distribution. Numerical solution let us make conclusion that temperature is close to Doppler limit reaches when all waves have the same type of polarization. For example, at the second plot, all waves have circular polarization, and at the third plot, all waves have elliptical polarizations. In this case, temperature is near to a Doppler limit. And when we have circular polarization for second field and for first field and for third field and and second field has linear polarization, temperature exceeds Doppler limit. In general case, system has 64 algebraic equations. However, it is possible to get precise analytical expressions for light pressure force and diffusion. As you can see, this plot, the obtained results, the obtained analytical expressions satisfy the results of numerical solution in the limit of low intensity of light field. In considered configuration, cooling temperature is defined by this expression. It depends on saturation parameters for each of the waves and detunings from resonance. And we can use obtained result to solve the task of optimization of parameters of laser cooling precisely for the case of linear polarizations. As you can see at the first plot, temperature reaches Doppler limit when all fields have the same intensity. And when you have different intensities, the temperature is bigger than Doppler limit. In that way, cooling temperature reaches Doppler limit when all waves have, when the tunings and intensities of all waves have equal values. As a result of the work, analytical expressions for light pressure force and diffusion were obtained. Optimization task was solved to achieve the minimum value of laser cooling temperature of ytterbium ion in polychromatic field. The exclusion of magnetic field from the cooling interrogating cycle make it possible to suppress Zeeman shift below to the level of 90 to the minus 19 degree. So actually exclude them from budget of uncertainties for frequency standards based on ytterbium ions. Also, in considered configuration, it is possible to suppress shift related to second order Doppler effect to this level. So that's all I wanted to say about my work. Thank you for your attention. I'm ready to answer all your questions.
Thank you, Dennis, for your talk. Do we have questions? No, any questions? Okay, so let's take this opportunity to thank Dennis and the other speakers of this session, Matteo and Alexei again. And Vanderlei, do you want to say something to close the session?
Yeah, just to remind everybody that tomorrow we start again at 12 UTC time, and we have a presentation of a few papers as the last section of our seminar. So I hope everybody that's been frequently seeing the seminar come tomorrow for the grand finale. All right, thank you very much, and see you tomorrow.
Bye-bye.
Bye-bye.
Bye.